everyone. Again, welcome back to the latest lecture session. Again, a very quick recap. So we have been looking at an example relevant to the TCLP based approach, right, for designing a solidification and stabilization mix. So let's look at that one example here again. So TCLP, right, and here we had both lead at 5000 ppm, cadmium at 1200 ppm, right, and we were trying to design the relevant matrix or the different fractions, right. In that context, obviously we needed the design pH, right. So for that we looked at the solubility, right, and we chose some such pH out here, right. But again, different trials were required there to choose the relevant variable or relevant best suitable variable to be able to choose the optimum pH. But obviously there is no one particular way as we looked at it. There are different ways. Sometimes cost considerations can come into play and so on and so forth. So it depends upon the relevant aspects or variables. For example, you might want to give greater weightage to, let's say, the toxicity of that particular heavy metal and such, and want to concern yourself with maintaining the relevant concentrations of a particular heavy metal at a lower concentration, let's say, right. Again, different aspects. So in that context, we ended up with the pH of 9.6 now, right. So let's move on to that acid neutralizing capacity test based table. So as we see for fly ash, and now the design pH is 9.6, right. So it's somewhere out here, right, between these two. So as you see at 10.5, the acid neutralizing capacity for cement is 16. And what is it for relevant range for fly ash? 9.6 is between these two values here. And as you see here now, the most probably this particular acid neutralizing capacity is going to be negative, right, as in this particular fly ash itself at what do we say 9.6 is going to be, what do we say, acidic or act as an acid, if you can say so, right. And same case with sludge at pH of 9.6, right, between these two ranges, right. It again does not have any acid, it can't neutralize an acid, but it itself acts as an acid in this particular range, let us say, right, and that is something that you can see out here. So by linear interpolation, right, between these three sets of values for cement, fly ash and sludge, right. Why is that? Because we are trying to go to look at finding the acid neutralizing capacity of this particular mixture, right. And what is that equal to? Obviously fraction of the fly ash into acid neutralizing capacity of fly ash plus fraction of sludge into acid neutralizing capacity of the sludge plus fraction of cement into acid neutralizing capacity of that particular cement. And obviously all this needs to be equal to 2 milliequivalents per gram, right, of your particular what do we say, per gram of your mixture, right. And obviously here there are obviously assumptions that even when we mix this stuff up, that the acid neutralizing capacities are going to, what do we say, obey the relevant what do we say, additive rule, let's say, if I may call that we are looking at here, right. So again, and also you can obviously add more what do we say, relevant, more of these relevant constituents such that your acid neutralizing capacity is greater than 2 milliequivalent per gram. But what does that mean? As you can see, sludge does not have any acid neutralizing capacity, neither does fly ash at pH or the design pH. So what does it mean? You need to increase the cement content, but obviously cement content, to increase that you need to what do you say, put in more resources or money. So thus typically people try to design it in such a way that you more or less meet the acid neutralizing capacity requirements from the TCLP point of view, right. Again, that is something that we look at, right. So let us look at the relevant cases and again the relevant aspect of problem 2. So this is what we have here, right, 2 milliequivalent grams. This is the amount of acid that you put in per waste in the per weight of waste in the TCLP test, right. So moving on, let us say again linear interpolation. So based on 16, right, at 16 we had what do we say, at pH 10.5 we had 16, right, and that is something that we see out here, and at pH 8.5 we have 20, I believe, right, and we are trying to find what it is at 9.6. So it is just nothing but linear interpolation, right. To just write it in a better format, it is 16 minus 20 by 10.5 minus 8.5 or you can say the slope or the rate at which it is changing into the actual range that you are looking at is at 9.6 minus 8.5, right. 16 is the one obviously at pH 10.5, right. 16 is the acid neutralizing capacity at pH 10.5, right. So, negative because 8.5 or 9.6 is lesser than that, but obviously the acid neutralizing capacity is greater or increasing with pH. That is why you obviously see that at pH 9.6 I end up with what do we say, acid neutralizing capacity for cement is something that I end up at as 17.8 milliequivalent per gram. Then for fly ash, as we observed, let us say I thought it might be negative, but let us say it is not. So, 0 right at pH of 10.8, right. What do we have here? 0 plus 0 minus 2 by 10.8 minus 7.8 into 9.6 minus 10.8, right. So, again we have a linear interpolation here. So, other than expressing it in this way, we could have also we can also express it as 0 minus, let us say 0 minus 2 by 10.8 minus 7.8, right, and then what is this here, 10.8 minus 9.6, right. Again looks like we end up with the value of 0.8 milliequivalents per gram for fly ash anyway at the design pH of 9.6. That is your design pH here, right. So, that is what we have out here, yes. And then moving on to this acid neutralizing capacity of the sludge, what do we have? Same approach, right. So, if we can look at that at pH 7.7 looks like the acid neutralizing capacity is -1, and pH 9.8 it is obviously negative minus 2, and then we are trying to calculate it at 9.6, right, and that is why we look at that range here, and we end up with what do we say, an acid neutralizing capacity of minus 2 or minus 1.9 for the sludge, right. So, again what is the only what do we say matrix here, or which compound is leading to acid neutralizing capacity of the mixture here? You see that it is only cement. Both what do we say, fly ash and sludge obviously cannot neutralize the acid, but actually contribute to the acidic content, let us say at the pH 9.6, right. That is something that you see out here, right. So, now I can plug in the relevant acid neutralizing capacities, right, for these individual relevant what do we say mixtures, and then I can solve for this particular setup. So, solving for that looks like the amount of cement content is 0.18, fly ash is 0.12, and sludge is 0.698, right. Obviously cement by fly ash, right, and I think we mentioned that it had to be 1.5, and that is what you see here, 0.181 by 0.121. So, that should be hopefully be in the ratio of 3:2, right. I think divide by 6 and so on, let us say, and you can get there, and obviously the sludge here, I guess. So, let us look at the total binder content, let us say, okay, cement by sludge, that is something to look at. So, let us look at, we are adding what do we say 0.26 adding cement, pardon me, in the ratio of 1:4 for with respect to sludge anyway, right. So, the other aspect obviously fly ash to sludge 0.173, that is obvious, right, and total binder to the sludge, this is something that we are typically concerned with. So, as you see I am adding what do we say 0.433 of what do we say, or it is almost half, let us say, right. The total binder is almost as if not 50 same, almost the same as your particular relevant waste here, right, slightly lower though. That is something that people look at. Why is that? Obviously because to minimize your cost you want to have greater what do we say value of your particular waste, right, and lesser the value of your lesser the content of your binder here. That is something to keep in mind. Now, we are going to move on to that problem 2, and there obviously we were trying to look at, is there enough water content present, right, as you have seen here we did not consider any water content here though, right, but obviously we need water. Why is that? It is going to be apparent why we have not considered that here, let us see, right. Let us look at what we have. So, sludge contains 15% dry solid, obviously what does that mean? 85% is water. So this water itself, we were presuming that is going to contribute to the hydration of the cement. Let's see if that's going to be good enough or not. So fraction of water in the sludge, right, it's 85% of that fraction of sludge. So that's what I have here as a total here, right. And looking at it, the fraction of water by cement, it comes out to be, it seems 3.278, right, and we only need 0.45, right. Fraction of water is something we calculated out here, and fraction of cement is something we calculated in the earlier slides, and water by cement ratio now comes out to be 3.278, right. So that, as you can see, there is enough water present for hydration of your relevant cement now. So all this obvious excess water, let's say, which is not going to be part of or consumed by cement for its hydration, what's going to happen to that? It obviously is going to fill up the pore space in your cement or the solidified matrix now, right, and that can contribute to obviously diffusion and so on and so forth, right. So that's something to keep in mind here, as in if there was just enough water content for hydration, right, that might be the perfect way to go about it, let's say, or the ideal scenario. But as you, obviously as you see, the sludge has a considerably high quantity of water, right. Now that's going to fill up the pore space. That's something to keep in mind, or that's one particular take home message here now, right. So now let's move on to the relevant aspects, as in we are going to look at a minor case study with respect to two sites, and again this data is from open source. I am going to present the sources here obviously, but typically, you know, from the relevant EPA documents and so on and so forth, right, or the US EPA documents. Again, if I mean these examples were chosen based on the kind of data that were available. Obviously not all data is available online, right, but I chose those examples where, you know, relatively more data was available. So let's look at what we have out here. So again, Creosote Works Superfund site. Again, Superfund site, right, you know, it's one way that you know, the classification of what do we say, the priority of sites that need to be remediated in the US, right. They, depending upon the priority, they can classify it as a Superfund site. Yes, again ex situ treatment, right, obviously solidification and stabilization is something that they considered, but let's look at what are the relevant aspects here, right. So let's move on. What was it being used for? It was used for wood preserving, let's say, scale, full scale implementation and ex situ treatment, solidification and stabilization obviously, site description, this is obviously the key aspect. So 60 acres of marshy floodplain, right, obviously, you know, this is of critical importance now, it's in the floodplain zone, right, that's something to keep in mind, right. Facility treated wood from 1930s to 1981, and 1981, that's when I believe the you know, relevant site was discovered to be contaminated and so on and so forth. We'll look at that, and it was contaminated with both creosote and pentachlorophenol, right, and also dioxins. Again, these are remarkably toxic compounds, right, certainly dioxins, right, I believe they are also carcinogens. So surface soils are contaminated by these particular relevant aspects or contaminants, pardon me. So let's move on. So cleanup timeline, just to understand or get you an idea about, you know, how things were done, let's say, right. So let's look at that. So obviously it ran from 30 to 81, and then it was discovered that this particular site was contaminated, right, and then emergency removal action, some relief around 1983. Site was listed, I guess, or you know, maybe as a Superfund site, right, in 84. Site risk, initial risk assessment and so on, or remedial investigation, pardon me, and feasibility study. Correct myself there, site remedial investigation or preliminary more or less and feasibility study was done, and this is something that we discussed earlier, as in we obviously need to understand you know, what are the relevant aspects involved here. And here obviously a focused remedial investigation, right, once you have some data from here. But again, as you can see, by now itself, I guess almost 12 years, more than a decade. And then risk assessment. Consider the risk assessment, that's something we looked at in the initial stages of our course, again 96. Record of decision, obviously this is a term typically used in the context of what do we say, remediation in the US, right. So again 96. So solidification and stabilization treatability studies, let's say, were conducted, again more or less batch studies and so on and so forth, right. So before you design or you know, implement your solidification stabilization full time, obviously batch or pilot scale studies need to be conducted, so they were conducted. So you know, then it was took a year, let's say, to be awarded to the relevant authority, right, or 2 years. And but as you can see, you know, the construction relatively is faster process, because you just need to be able to mix the relevant system, right, and get the things done. typically solidification and stabilization, that's the relevant aspect out here. But as you can see, it took almost 2 decades for the various aspects to be done, at least even in the US though, right? That's something to keep in mind. And let's look at what I have here. So 2 aspects to highlight: US UPF focused risk assessment. So they chose 10 power minus 4 based on future industrial use scenario, right? So as we might have remembered, let's say, or to refresh our memory, let me go back to this particular aspect, as in when we look at risk assessment for lifetime cancer risks, right, we typically looked at 10 power minus 6 risk, right, to be able to see to it that the risk posed to relevant people there is not going to be greater than 1 in a million or 10 power minus 6. But for various reasons they considered 10 power minus 4, and this is something we looked at too, right? So, in some cases they also look at 10 power minus 4 thresholds, let's see. And also the scenario is that it's not used for, let's say, residential purpose or such, with the caveat that it's going to be used for industrial purposes, let's say. That's something, right? So that's something to keep in mind. And also the record of decision called for. What did this record of decision call for? Excavation, ex situ treatment by solidification stabilization, and replacement of treated soil under a cap, right? So it's not just that you are excavating it, treating it offsite and letting it be out there. Let's say you are also putting a cap over this solidified and stabilized what do we say, mixture here. That's something that people have done, at least in this particular site, right? Let's look at what else we have here. So 1998, obviously remedial investigation and feasible study. We are looking at the relevant aspects in slightly greater detail to understand how the decision making was done. So they looked at remedial alternatives and costs, right? So to secure the site and monitor, 0.3, excavate soil to 120 feet, it's 3,700, let's say, right? Again, this is millions, let's say, cost is in millions, right? And million is, I guess, 10 power 6, and keep in mind these are in dollars, obviously. 3,700 millions if you excavate the soil to 120 feet though. To cap and monitor it, let's say 25. To excavate the soil to 5 feet, 157, compare that with 120 feet. And solidification of soils to 2 feet, it's 34. Incineration was considered, that's again 260. Soil washing, solvent extraction, and bioremediation, different aspects of here, right? But obviously the key aspect is solidification of soils to 2 feet, again maybe in situ, I guess, right? But that wasn't clear from the data that we had. It's was 34, let's see, right? Again, that's something to consider here among all the other alternatives here, right? So if it is just securing the site and monitor, yes, 0.3, but obviously if it's within, as we remembered, or we looked at it, pardon me, it's within a floodplain, right? So this probably is going to be relatively difficult to get done, right? So this is what we have here. These are based on the preliminary studies. So after completing this study, the EPA reduced the amount of soil requiring treatment from these many what do we say, cubic yards to 45,000 cubic yards, right? 1,94,000 to 45,000, almost, let's say, what is it now, 1/4 of it, right? So decrease the volume of soil that had to be what do we say, treated from what do we say, 2 lakh cubic yards, let's say, to 50,000 cubic yards. Again, there were 2 aspects. One obviously was that more detailed site investigation was conducted to see which particular area was more contaminated. So obviously you need to put in money in the initial stages to for site characterization, and this is something we have seen either during natural attenuation or permeable reactive barrier and so on and so forth, right? And the other key aspect was that they also decreased the risk from, let's say, residential risk to industrial risk, right? So again, what are the aspects here? So risk, let's say, was 10 power minus 6 typical values that you look at, especially if it's classified for residential usage. Industrial usage, let's say 10 power minus 4, right? So one of the aspects is that by reducing the what do we say, thresholds, let's say, to treat it to this threshold, more soil had to be treated, and as we saw, the costs are relatively high, and thus obviously they decrease the thresholds, obviously affecting the relevant costs, and also, let's say, precisely defining the extent of soils of concern or better site characterization. So these 2 aspects, a management decision was taken, right? And let's look at what else we have. So comparison between the 1998 remedial investigation and feasibility study with the 1996 record of decision, let's see, right? So here remedial technology solidification, and again solidification was considered. Initially they thought residential, but finally it was decided to be industrial, and initially it was thought to be this volume or 2 lakh what do we say cubic yards, but finally they decided on 45,000. Average depth, yes, they let it be at 2 feet, right, and estimated cost from 34.4, now they end up with 4.5 obviously, right. This is something that to keep in mind, and again if you remember, this particular value was the lowest among all the other alternatives, considering let us say the other than the one except for monitoring, I guess, right, for closing the site and monitoring. So this was the one that was the lowest, and now they obviously brought down further by decreasing the quantum of the soil that needs to be treated, right. So that is something to keep in mind. And what else do we have here? So based on the 2 studies, the ROD let us say defined this particular what do we say contaminated soil to be the principal threat, as in you still have some contaminated soil other than this 45,000 cubic yards, but that was again due to different factors, probably the cost let us say, and relatively less risk posed to the relevant populations or estimated population let us say due to that particular level of concentration, right. And also action level goals. So here the contaminant action level, as in this is the level of contaminant in soils at or above which remedial action is required, right. This is A out here, and B is based on the lifetime cancer risk future for an adult worker, and the risk is 10 power minus 4, right. So set action level goals, right, and action level B based on this particular case, they want to bring it down to 225 milligram per kg of soil, milligram of arsenic per kg of soil, and benzopyrene, dibenzoanthracene, pentachlorophenol, and different dioxins. Obviously, as I mentioned earlier, dioxins are remarkably carcinogenic or pretty potent, and obviously you see that is the reason, one of the reasons why they want to bring down the concentrations here. Again, these are the action levels or these goals that they want to, that they set based upon the risk of 10 power minus 4, right, carcinogenic risk obviously, right. So let us move on. So EPA's National Risk Management Research Laboratory conducted the laboratory tests or the bench scale tests or the treatability tests as they are calling it, to establish that solidification and stabilization treatment can be effective for these contaminants of concern, right, and also evaluated the different formulations, as in different binders were looked at, let us say different admixtures and so on, and then they developed the approximate costs again for the solidification and stabilization, right. And the treatability studies demonstrate that obviously it is effective and that the costs were within a reasonable limit here, right. So obviously initial estimates, and then you based on these initial estimates and different factors, minor modifications, and they brought it down, as in the volume of soil to be treated and so on and so forth, and then bench scale studies were done, and then again is that feasible again, or to what extent are our prior assumptions relevant or so on, and that is worked out, and we see that it is within reasonable cost, let us say, right. And here we have successful stabilization formula for the different for this particular site, right. So these are the different reagent additions, weight of the reagent added after what we say after addition of reagent to weight of untreated soil, let us say, right. So treatability test formula, different costs here, 39 to treat 1 ton of soil, this is the what do we say cost that is required, let us say, for this treatability test formula, or different types of formulas that we have here, as in with just untreated soil, Portland cement, the ratio to the untreated soil is 2 to obviously 0.2 by 1. So they what are the different binders that they considered now, and what are the different ratios that they considered. Different binders were Portland cement, fly ash, they also considered activated carbon. So it seems they also use some proprietary reagents, right, from this particular relevant company, right. They use proprietary reagents probably to enhance either maybe the degradation of these toxins, or the binding properties of these particular binders, let us say. And then dilution factor, right, excluding water, let us say, which is weight of untreated soil plus reagents divided by the weight of the untreated soil. So this gives you an idea about the total amount of binders that obviously need to be put in, let us say. So here it is 0.32 is the amount of your binders and the other additives that you are putting in, and 1 is obviously the weight of your solid, right. So that is what this means now, 1.32 is the total weight of your particular binders, admixtures and soil, and 1 is the weight of your particular untreated soil, right. These are the different fractions and they looked at different costs obviously, right. So, let us just try to analyze this particular aspect and then this case obviously you see that cement is relatively what we see in lesser fraction compared to this particular case, right, and that is how they looked at it. Obviously, you know, when they considered the case when they use the proprietary reagents, right, you have the cost to be considerable even though the cement and fly ash is negligible, right, that is something else. So, let us look at what they ended up with though, right. So, soil from 7 acre, right, was excavated for treatment that we are aware of, and now they ended up with this particular case where they used waste, cement, fly ash and powdered carbon, right. So, let us look at what that is, probably waste, cement and powdered carbon probably in this ratio, but we need to check those out. So, they did not choose this, they choose either particular this option or this option, right. So, we can check the relevant cases based on the fraction of these particular Portland cement to fly ash. Here that is double and here it is more or less the same. So, let us see which option they chose. So, it is 5% same. So, obviously they chose the B one, I guess, right, the one with the least cost, right, that is something to keep in mind. Obviously, we had you know, the relevant laboratory looked at 3 aspects, one with different fractions of fly ash, cement and so on, but the differential factor was that the cost was higher for one and lesser for the other. And there was another aspect where they looked at what do we say, binders from, let us say, or proprietary binders, let us say, from a particular company, and again the costs were high though, right. So, they chose that particular one which was relatively cheaper now. And again we are going to continue this, but you know, looks like I am out of time. So, we will continue this in the next session. But what we have looked at so far is, you know, more or less a logical what do we say, process of decision making, initial site investigation, right, and then based on that what needs to be done was decided in the record of decisions, and then the bench scale studies, right, where they again evaluated different matrices, right, which is what we just looked at, and then choosing one particular matrix and then implementing that, right. But again we are going to continue this in the next session, and thank you for now.